This is a time lapse right now.
Are we good?
Yes.
Let's bust this out. So waves on strings, a few rules that we've got to have for like always waves on strings. To have a wave on a string we have to have it under tension, and to get it under tension we have to have the two ends fixed. Like a floppy string you can't have a wave on, right? And so because the wave is fixed at the end, we know that as a wave goes in and reflects off that fixed end, what happens to the reflected wave? It's always inverted. That means that the incident wave interferes with the reflected wave. Because it's inverted, they interfere destructively. Because they're the opposite to each other. It's reflected and flipped upside down. And that means that always at the fixed end, no matter what, there's always going to be a node, because the incident wave is always going to interfere destructively with the reflected wave to cause a node. And somewhere in the middle we have to have at least one antinode, and that's where the reflected wave and the incident wave are interfering with each other constructively. Works. So what's a node? What's an antinode? So a node means nothing. Like node's kind of an alternate word for zero. So a node is where the wave hasn't displaced the medium from its equilibrium position at all. It's just at the equilibrium position. So a node is nothing. An antinode, like an anti-nothing, is a something. So it's where the wave is displaced by the maximum amount from that equilibrium position. And so these are the waves that we just managed to bust out on our one-stringed guitar there. We've got to give these names, right? And so this one here is like, it's the fundamental frequency. Okay, it's the one that if you don't do anything to the string and you just pluck it anywhere, you make a bajillion different frequencies, but the only one that's picked out by the wave to resonate is the one that fits, that causes exactly a node at each end and an antinode in the middle. It's the one where the wavelength is the frequency that has a wavelength that's exactly twice as long as the string length. Frequencies. The other name for it is the first harmonic.
What? That's not.
The first harmonic, it's called.
Really? Is that what it's called?
That's what it's called.
Okay.
And on this one, the length of the string, the wavelength, is equal to 2 times the length of the string. We can just see that from the picture. This one here, what harmonic might that be?
Second.
It might be the second
Okay.
harmonic. And if we wanted another name for it, we might call it the first overtone. Because it's the first tone over the fundamental. It's like the next highest frequency that you can possibly
Third
name.
harmonic.
How long's the wave compared to the string?
Exactly.
One. So the wavelength is the string length. What might we call this one?
Third harmonic. Second overtone.
Third
And
harmonic, second overtone.
And first something else.
How can we compare the wavelength and the string length? So the string length is 1.5 wavelengths.
Yeah. That's true.
3/2 is nicer than 1.5, because then it's really easy to rewrite it to say that the wavelength is 2/3 of the string. What about this one? What's this?
What comes up with 3?
Third overtone. Fourth harmonic. How does the string length compare to
Or half.
2.
half? So the wavelength is the string length over 2, or the string length is 2 times the wavelength. And the last one is the
4th overtone.
fourth overtone.
excellent.
And how do we compare the wavelength to the string length?
Isn't it 2 and 4?
It's 2/5 of the string length is the wavelength.
Yeah.
So 2.
Because we do it in sections, it's got 5 sections, 2 sections is 1 string, so it's 2 at 5.
And so what does wavelength equal?
Only one wavelength.
Sorry, what is the string length?
5/2.
Cool. And so the real skill, the thing that we need to be able to do, the thing that might ask us to do in our exam is like this, I don't know, the third harmonic is played on a string, draw a picture. So we have to be able to like link the names of these different things to the picture of the wave and do a calculation. So we have to be able to use those pictures to kind of write down these equations. And so it's really useful. What I find useful is when I look at them, I think like, what does a whole wavelength look like? So in my head on this one, I'm like, oh yeah, a whole wavelength goes out, it's twice as long. This one is a whole wavelength. On this one, that's a whole wavelength. On this one, that's a whole wavelength. And then like this, I can look at that, I'm like, oh yeah, one wavelength is 2/3 of the string length. It just makes it really easy to write down those equations. So just as you're getting confused and complicated, just think, what does one wavelength look like? It's got one up there and one down. So the pitch difference, if we halve the wavelength, what's going to happen to the frequency? It's going to double. And if we make the wavelength a third, the frequency is going to be triple. So if we called this one F0, this would be 2F0, this would be 3F0, 4F0. And F0's like the symbol, could be the symbol for the fundamental frequency.
Oh, okay, it's 3 times.
Pitch is frequency. Pitch means frequency. I've just added on here the antinodes, which are the big bits where it's spread apart, and the nodes, which is the little bit, the destructive interference. So always a node at each fixed end, and at least one antinode in between.